In the previous videos for Chapter 4, I introduced script files, showed you how to create and run them, and talked about using comments to document your script files. In this video, I'll introduce some convenient touches you can include in your script files so that you can make them easier for other people to use. For example, if you're writing code for users who have no programming background, your code can prompt the user to input a value using the keyboard, rather than have them edit a file to change a value. You can also display results from your files with much nicer formatting than simply letting MATLAB use the default formatting to display variables. You can have your MATLAB program prompt the user to input a value from the keyboard while the program is running. The MATLAB command to do this is input. This is the syntax. The input command accepts a string as an argument. When the command is executed, this string is displayed in the command window and the program's execution stops and waits for the user to press the enter key. While the program is paused, the user can type a response to the prompt that appeared in the command window. Once they've typed their response, they press the enter key. Once the enter key is pressed, MATLAB's input command reads the information the user typed. In this syntax above, this result is assigned to a variable named var. Now var is a defined variable and the program's execution continues. I'll use the script file from the second Chapter 4 video, which calculates beam deflection, to illustrate how this works. I'll use the same folder that I used in the previous video. It was named Chapter 4 in the MATLAB Demos folder inside the TIM folder on the C drive. I'll make this my working directory for this session too, since it'll give me easy access to my previous file. So to set that as my working folder, I can use the cd command and specify the path to the folder. So I'll type cd space c:\/ for the root of the C drive, tim to get to the TIM folder, / MATLAB demos, / Chapter 4. The file I created before was named beam.defl, so I'll edit it by typing edit beam.defl. Now the file is ready for me to edit. I'll change the program to allow my user to input a value for x. My command will be x equals input, open parentheses, and then the message I want to display in quotes. So single quote, input a position in inches. Maybe a colon, a space, then I'll close the single quotes and close the parentheses. Remember that strings are defined by typing the desired characters in single quotes. They'll show up in purple in MATLAB's editor. Now I save the file and then run it by typing the file name at the command prompt. The input command asks me for a position and waits until it receives an enter keystroke. I'll type 2 and press enter. The beam deflection is calculated and displayed. Inputting data interactively can create some problems, however. Sometimes the user can make a typo and not realize it, so they'll get a wrong answer and have no record of how it was created, since once the MATLAB session is closed, the value they input was lost. In order to make sure that my user retains a record of the workspace, I think I'll have my program save the workspace to a file. So I'll add another input command to prompt my user to input a file name where the workspace will be saved for future reference. My command's going to be fname, which will be the variable to which the file name is assigned, an assignment operator, input, open parentheses, single quote, the message I'm going to display, which is type a file name to save the workspace, close single quote, a comma, then an S in single quotes, and close the parentheses. The S in single quotes is an option that tells the input command that the user input is to be treated as a string. Alternately, you could provide your user instructions that they should put the file name in single quotes when they type it. But remember that the goal here is to make using your program easier for them. Okay. After that command, I'll use the save command to save the file. The command will be save, open parentheses, fname, close parentheses. This will save the entire contents of the workspace to a file on disk. This may be overkill for what we want, but at least it ensures that the user has a record of their work. If you did want to save only the variables associated with this analysis, you could list the variables to save in the command itself. If I were doing this for real, I'd probably save W, E, I, L, X, and Y to the file and nothing else. Now I'll save the file and run it. I'll input X equals 5, and I'll set the file name to my file. The file gets saved to the current working directory with the name that I specified. I can see this in the current folder window or by typing ls at the command prompt. I can check the contents of the file by clearing the variables from the workspace. Then I'll check that the contents of the workspace with the who command. All my variables are gone. Now I'll load the file with the load command by typing load space my file. I can check that my variables got loaded by typing who, and there they are. You can also customize how you display your results in your script file. There are a few different ways to do this. First, I'll show you the easiest way, using the disp command. To use the disp command, just type the function name, disp, and then what you want to display in parentheses, either a string or a number. The value will be displayed in the command window. The argument to the disp function can be either a string or a number. Numbers, of course, are usually referenced by their variable names. Sadly, you can't mix strings and numbers in a single disp argument. But you can get around that problem by combining multiple strings into a single string. There are two easy ways to do this. Just put a list of the strings within square brackets, or use the strcat command with a list of the strings as an argument to the command. In either case, the strings get combined in the order they're listed, so the final string will start with string 1, the next part of the result will be string 2, and so on. This trick, along with another MATLAB command, allows us to display both strings and numbers in the same disp command. You can convert a string to a number with the num2str command. This command accepts a number as an input and returns a string that looks like that number. So if we have a variable named var, which happens to be, say, 3, and we type the command num2string of var, we get back a string that looks like a 3. So this command can be substituted among these strings using this syntax. This whole string can then be used as an argument to the disp command. Let's take a look at how this works with the example script file we used in our last demonstration. First, I'll add a semicolon to the calculation of the displacement to suppress MATLAB's default method of displaying the results. Now I'll display the results using the disp command. I could do this in several commands by typing disp, open parentheses, the string I want to display in single quotes, the calculated displacement is, I'll use a colon, close the single quotes, close the parentheses. Then I'll use the disp command to display the displacement itself, disp, open parenthesis, y, close parentheses. Since y is a number, it doesn't require the single quotes necessary to display the string. Finally, I'll put the units on here. Disp, open parentheses, quote, inches, close the quote, close the parentheses. Now save the file and run it. I do get a descriptive message and the value I want. This lacks a certain something though. Let's try putting all the information on one line. I can do this by modifying my previous commands to be disp, open parentheses, and open square bracket within which I'll place a set of strings that will all be concatenated together. So the first thing I'll display is, quote, the calculated displacement is, single quote to end that string, a comma. Now the next part of the string is going to be num2 string of y. So the number y is going to be converted into a string there, a comma. The final part of the string is going to be quote, space, inches, close that quote. Now close the square brackets to indicate that I'm done concatenating strings together and close the parentheses. Save the file again and rerun the command. I think that's better, since it's easier to match values to the descriptions, and your user doesn't have to know what variable name you use to present the displacement. Finally, if you have a lot of numbers that you want to display in an organized way, like a table, you can use formatted output. The command I'll use here is fprintf. Its arguments are a code to provide the format of the items being displayed and a list of the items to display. The code always starts with a %sign. It can be followed by a conversion code, field width, precision, control characters, and some other generally optional codes and flags. Now I'll talk just a little bit more about the codes that can be put in these places. The conversion codes provide the basic type of information being displayed. For example, the code I is used for signed integers. F is used for fixed point values. There are plenty of other codes. U is for unsigned integers, E is for exponential notation, and so on. We can also specify the field width and precision. The field width specifies the total number of characters being displayed, and the precision specifies the number of digits to the right of the decimal place. For example, the number 12.5 here results in 12 digits being displayed, with 5 to the right of the decimal place. Keep in mind that one character is used for the decimal place itself, so there are actually 6 digits to the left of the decimal place. This code goes between the %sign and the conversion character. Another common code to include is a control character. These controls adjust the display and are also used to display special characters. For example, one special character is a %sign. Since a % is used as part of the command, we need a special way to actually display a %sign. Examples of control characters are /t for a tab and /n for a new line. I've only shown enough of the available options here so that I can do a demonstration using MATLAB. There's a slightly more complete but still limited list of codes in the text material for the course. The MATLAB documentation, of course, gives you a comprehensive list. Suppose I want to display all of the values used by my beam deflection program after the code runs. Using MATLAB's default display, or the display command, will get sort of awkward, since a lot of material will scroll past with more white space than is really necessary. In this example, I'll show how the fprintf command might be used to improve things. First, I'll get rid of my old disp command. I'll also delete the save command and the prompt for a file name, since I don't like typing in a file name. I'll replace those with 2 fprintf commands. The first command will put some labels on the screen so that the user can tell which number corresponds to which variable. My labels are going to consist of only one character, but I'm going to reserve space for 7 characters in each label. This is because I'm going to use 7 digits to display each of the numbers. So also using 7 characters for the labels will help line them up with the numbers below them better. The labels will be strings which have a conversion code of S. So I type fprintf, an open parenthesis, a single quote to start the string that gives the formatting for all of the letters that I'm going to display. So the first thing I'm going to do is tab over, \t. I want 7 characters, %7 with an S to denote a string. Now, all of these characters are going to share the same formatting, so I just have to repeat this 5 more times for my 6 variables. Now, when it's done printing this, I want to move to a new line so that the values will be below the labels. That's a \n. Now I close my quote. That's the end of my codes. Now a comma and the list of things that are going to be put in those codes. So quote E, close that quote, comma, I is next, so quote I, close quotes, comma, quote L, quote, comma, W, enclosed in quotes of course, comma, X, and finally the displacement itself, comma, quote, Y, quote. In the next command, I'll print out the associated numbers. So fprintf, open parentheses, quote, I'll still want a tab between each of my numbers, which will help them line up with the labels above them. So \t, %7, I'm going to always be using 7 digits. The first one, I think I'll display 2 digits to the right of the decimal place, so 0.2, and I'll put it in exponential notation, which is an E. Now another \t to tab over to the next number, %7. I think this time I'll use 3 decimals to the right of the decimal place, so 7.3, F for a floating point number, \t, the next one will be %7, 0.2, I'll show 2 decimal places on this one, F, \t to tab over to the next number, %, 7.2, F, \t, %, 7.2 F again. Now I'm finally to my last number, which is the displacement, \t, %7. The displacements are typically pretty small, so I'll put 5 digits to the right of the decimal place. So 7.5 F, and then go to a new line again, \n. In the single quote to stop the formatting codes, then list the variables that I want to display, comma, E, comma, I, comma, L, comma, W, comma, X, and finally, comma, Y. Close the parentheses. Now I'll save the file again and run it. I get a pretty nice little table displaying my results. If I wanted to be fancy, I could include a better description of the values instead of just showing the variable names, and maybe also add a row showing what units are used. With script files, we're finally starting to use MATLAB somewhat efficiently. Commands don't have to be executed individually, and it's easy to keep a record of exactly what was done, which can be really important for an engineer. Modifying our approach to solving a problem is also easier. If we want to change something, we can change the affected part of the script file and rerun it. If we've made the file self-contained, it's nearly effortless. In the next few videos, I'm going to introduce arrays and we'll begin to use MATLAB as intended. Engineers use lots of numbers. Arrays are organized collections of numbers, and it's natural to set up many engineering problems in terms of arrays. MATLAB makes array operations really simple. So, in the next chapter, I'll start using some MATLAB capabilities which have made it so popular among engineers.